Hello, I'm Mario, and this is the video presentation of my final project for graphics, Space Invaders. The core gameplay loop is simple. Destroy the aliens before they either destroy you or they reach the bottom of the screen. As you beat more levels, their speed, and thus the difficulty of the game, increases linearly. To create this, I used a variety of key abstractions, such as game objects, game object pools, colliders, and events. Game objects are the building blocks of the game and provide a rendering aid, as well as specializable functions that our program manages, such as the update function, which runs once every frame. For example, this spaceship uses the update function to check player input and move accordingly. Colliders and events go hand in hand. Colliders are generic shapes that represent the interactive volume of an object. This game has three types of colliders: sphere colliders, box colliders, and ellipsoid colliders, which are what bullets use. Colliders must be registered in at least one collision layer to work. Collision layers are groups of colliders that may collide with other layers. We will go in depth on collision layers when we talk about the collision detection algorithm. Lastly, events. Events are how different components of the game talk to each other agnostically. Event-driven programming is very powerful because it allows us to extend the application very easily. Collisions are processed via the onCollisionEnter event that every collider provides. For example, when a bullet collides with an alien, the alien, who is listening to its collider's onCollisionEnter event, promptly dies and also invokes its own onAlienKilled event, which the main program is listening to create an array of burst particles at its location, matching the alien's color. Without further ado, let's go into code analysis. So taking a look at collision layers, we will see how you can add colliders, remove colliders from them, or tell the collision layer that it should collide with a specific other layer. On collision prep, which we run before running any check collision functions, we first order or sort the entire array of colliders by their beginning X component, their lower X component of their bound. We will look at colliders later to go into specifics of how this bound is calculated. So when we run over collision layers for check collisions, we check every other layer that this collision layer can collide with, and then we check the colliders of this collision layer in order of their x-axis, which allows us to actually be really efficient about it, because we will only check whether two colliders can collide with each other if their bounds at least match on the x-axis. If it is possible, they would collide in the x-axis. This is something similar that we see in merge sort in the natural merge part of the algorithm, where we take two sorted arrays and we check in which order they are supposed to be placed. This is a little bit more complicated because we're not working with single values, but with ranges of values. But it works intuitively in a very similar way. So after we have assessed whether two colliders can collide at all, we check the specific colliders collides with function. Now, collides with is a generic way of checking collisions between two colliders, which does the following. It requests a list of probe points from one of the colliders and checks if the other collider contains any of those probe points. It does the same in the other direction, and if any of those probe points happen to be in the other collider, it returns true. Now, getProbePoints and contains are two functions that are overridden by every type of collider. So for example, box colliders, getProbePoints returns the list of corners, for example, that is not exhaustive and that can lead to some slight edge cases, but in practice it is fine. And contains just checks whether the point is in a bounding box. Contains is perfect in every case. For example, for sphere colliders, the probe points are the points at the top, left, right, far end, close end, and bottom end of the sphere. And it is the same for ellipsoidal colliders. Now, get contains simply does the mathematics of, for example, if a sphere checks if a point is close enough to the center of a sphere, and for ellipsoids, it first scales the point depending on the ellipsis, and then checks whether it would be inside a sphere of the corresponding radius.